Hello friends, this is Salil here. At this time of crisis due to corona pandemic, I assure you that I'll continue to provide you resources for learning. So here is the lecture 2 on determinant. If you have not watched the lecture 1 on determinant, which was the first lecture, the link is in the description. Stay safe, stay home, stay online, and remember that there is no short route to success. Well, it is the second lecture on determinant. We have discussed the properties of determinant in the first lecture, and today I'll be taking few examples on the application of properties. Since it is online content, so for the sake of saving time, I'll not be holding the screen after displaying a question. So you can pause the screen whenever it is required and take down the question. This is the first question. Expand the determinant. The first row is ABC, BCA, and CAB. Also known as, this determinant is also known as circulant determinant. Circulant determinant. This is very frequently used determinant in several topics. So let us dwell upon this determinant and expand it. Well, the easiest way we can afford to expand this is by rule of Saurus, which we have discussed in the previous turn. If I recreate the two columns, column 1 and column 2, once again and write it separately, then you can see that it will read as A, B, C, and B, C, A. Right. Before I expand this, let me tell you how this determinant can be remembered. Well, if I draw a circle and write ABC at 3 places on the circumference in anti-clockwise order, A, B, C, then they are nothing but they are the anti-clockwise rotation of 3 numbers starting from each one. Like the first row is ABC, right? Can you see that the first row is ABC? The second row is BCA. Is it BCA? Yes, it is BCA, right? And the third row is CAB. Is it CAB? So that is why probably it is known as circulant determinant. Anyway, as far as expansion of this is concerned, you can see that by applying the Saurus rule, we can reproduce the column 1 and column 2 beside the determinant. Now all 3 principal diagonals would be taken positively. This diagonal, and this diagonal would be written as positively, whereas all the 3 secondary diagonal would be negatively included. So this diagonal would be negatively included. If you can undo the drawing, you can see at once, right, the 3 principal diagonal being ABC. So this is gonna be equal to ABC. Again, you can see that the second principal diagonal is, it is the second principal diagonal. This is again ABC, isn't it? So again ABC you have, and the third principal diagonal is again ABC. You can see that, right? So third principal diagonal is also ABC, whereas all the secondary diagonals will be negatively included. That's why you can see that the first secondary diagonal is this. So C into C into C, that is gonna be C cube. So minus C cube. The second principal diagonal is A into A, which is gonna be minus A cube. And the third secondary diagonal is gonna be B into B into B. So that is minus BQ. If I rearrange this, I can write it as 3ABC minus A cube minus B cube minus C cube. Well, this is the first way in which determinant can be written. There are four different ways. If I call this determinant as delta, so we have seen that the first value has come out to be, that is 3ABC minus A cube minus B cube minus C cube. Now, again, this delta can be written in three more different manners rather. The next one can be, it can be factored, you have seen in the basic classes that it can be factored into A plus B plus C, right? A plus B plus C into A square plus B square plus C square minus AB minus BC minus CA. This is the second form. The third form is the same thing can be written as, if I multiply this by 2 and divide this by 2 as well, so this can be written as minus A plus B plus C by 2, or rather 1 by 2 can be written outside, right? And now the 2 which has to be multiplied can be multiplied in the second bracket, and you can see with little thinking that the second bracket will become A minus B whole square plus B minus C whole square plus C minus A whole square. This is the second way. Now, rather third way. Fourth way in which it can be written is, I do not multiply with 1 by 2 and 2, and this becomes what? This becomes A plus B plus C. Minus is sent inside the second bracket, and the second bracket renders into a factor which can be written as A minus B into B minus C plus B minus C into C minus A plus C minus A into A minus B. Right? So these are the four different manners in which this circulant determinant can be written. So you take a note of it, and this is very useful determinant. It is very frequently used in several topics. Well, this is the second question, and this was asked in JEE 1998. Here they're asking that if this determinant is equal to x plus iy, then x and y will be equal to. So this determinant is 6i, where I is square root of minus 1, minus 3i, 1, 4, 3i, minus 1, 23i is equal to x plus iy. Now you can see that if I go for the operation, a property of determinant, any row, multiple of any row can be added to any other row without altering the value of the determinant. And thus, if we add row 2 to row 1 is modified as row 1 plus row 2, then we get row 1 as 4 plus 6i. After adding row 2 to row 1, we get, can you see that 3i and minus 3i become 0 after adding? Minus 1 and 1 becomes 0 after adding. So the first row becomes this. Now you can see that it has become a very simple determinant because we can expand the determinant by any row or any column. Now if we expand the determinant by the first row, so needless to say that there are two zeros. That's why only one cofactor is to be evaluated, that is 4 plus 6i. So we expand it by the first row and we get we get 4 plus 6i. The cofactor of this would be 3i into I minus principal diagonal minus secondary diagonal. So this would be the principal diagonal. Will it be or not for the cofactor of 4 plus 6i? And this will be the secondary diagonal. You can see that the principal diagonal would be 3i into I and minus the secondary diagonal would be 3 into minus 1 is equal to x plus iy. Now you can see that this remains 4 plus 6i. I don't have to do anything with that at all. And this becomes I into I square is minus 1, that's why this becomes minus 3. And minus into minus becomes plus, that's why 3 is equal to x plus iy. Can you see that the LHS vanishes? 0 is equal to x plus iy, and thus I get what? X is equal to 0 and y is equal to 0 both. Because here the real and imaginary both part are 0, so x and y both will vanish. So my correct option would be D option. And that is the answer to this question. Well, this is the third question. It was asked in I.I.T. JEE 1981. Here, a determinant involving x has been equated to 0, and you have to find the roots of the equation. Now, the first question is, what is the degree of this equation? You can see that no two element making a term of the determinant can be picked up from the same row and same column. That's why these two will never get opportunity to get multiplied. These two will never get opportunity to get multiplied. That's why the highest degree in the expansion of this determinant would be x square. That means it is a quadratic equation. So that it will have only two roots. Exactly two roots, neither less nor more. Now, you can see that if I put x is equal to 2, let me copy the determinant once again. So probably I do it here. 1, that is 1, 4, 20, 1 minus 2, 5, and 1, 2x, 5x square, right? Now, you can see that this has been equated to 0. If I put, if we put, it is trial and error, x is equal to 2. What do we get? You can see that determinant becomes 1, 4, 20, 1 minus 2, 5, and 1, 2 into 2 would be 4, and 2 square would be 4, that's why it would be 20. Can you see something beautiful here? The first row and third row become identical, and it is one of the property of the determinant. If any two rows or columns are identical, then the value of determinant vanishes. That means yes, x is equal to 2 is satisfying the equation represented by the determinant. That's why x is equal to 2 is the root of the equation. That's why x is equal to 2 is the root. Implies that x is equal to 2 is a root. Right? Now, if we put, let me create some space. If we put x is equal to minus 1, you can see what the determinant becomes. Determinant becomes 1, 4, 20, 1 minus 2, 5, and 2 into 1 is 2 into minus 1 is minus 2. Minus 1 square is 1 after all. That's why 1 minus 2 and of course 5. Can you see that? Again, we can see that the row 2 and row 3 become identical. And you know that when two rows are identical, then the value of determinant vanishes. So thus x is equal to minus 1 appears to be again the root of the equation. That's why this will vanish and implies that x is equal to minus 1 is the root. Since it is a quadratic equation which is represented by the determinant, it will not have more than two roots. So finally the answer would be the root of the equation, the roots of the equation represented by determinant are x is equal to 2 and x is equal to minus 1. That completes the discussion of this question. Well, this is the fourth question, and now it is given that there is a determinant involving x which is equal to 0. So of course, this is the equation in x, and one of the root is mentioned, that is x is equal to minus 9, and we are required to find the other roots. See, according to Sarah's rule, uh, principal diagonal occurs in the expansion of determinant. So x into x into x will be a term in the expansion of determinant. That's why it is a cubic equation. It can't be more because there are only 3x occurring in the determinant. That's why, so let's understand that this would be a cubic equation ultimately, because this diagonal will definitely occur in the expansion of determinant. Once we say that, now one of the root is given, that means we are required to find two other roots. So if I copy the determinant once again and check it out, that is the determinant is x 3 7 2 x 2 and 7 6 x. As usual, if I expand it by the Soros rule, that is write two more columns beyond the determinant. The first column and second column is being replicated once again. So if I replicate these two, then I'm going to get what? I'm going to get, let me write with different color, x 2 7 3 x 6. So you can see that there'll be a term over here, principal diagonal, which is this, right? So this would be nothing but x cube, and then there'll be a term here. It is absolute after all, three numbers are getting multiplied. That is 3 into 2 into 7. So that is 42. That is 42. And the third term is 7 into 2 into 6. So that is 84. 7 to the 14, 6 is 84. So we have 84. And truly we don't need to write the secondary diagonal. Even then, let me write the secondary diagonals. And the secondary diagonals would be, that is minus 49x, minus 49x, minus, you can see that, 12x, minus 12x, minus 3 into 2, that's 6x, is equal to 0, which becomes x cube minus 67x plus 126 is equal to 0. Now, if the roots are, let's say roots are alpha, beta, and gamma, so already it is given that alpha is equal to minus 9. Now, what is the sum of the root from the theory of equation? Sum of the root is minus the quotient of n minus 1 degree, that is x square in this case, because it is a cubic equation. That's why the next degree would be x square, which is absent. So because x square is absent, you can see that here x square is not there. Not there. Because of absence of x square, the sum of the root alpha plus beta plus gamma will be equal to 0, implying that alpha is known. That's why beta plus gamma which are required to be found is equal to 9. That is equation number 1, Okay. And product of the root is minus the absolute, that is a term which is not with x, right? Absolute term upon the highest degree coefficient. That's why the product of the root, that is alpha, beta, gamma, would be equal to minus 126. And since alpha is minus 9, that's why beta into gamma, let me write gamma neatly. Gamma is going to be equal to minus 126 upon minus 9, which is 14. Equation number 2. You can see that now we have come down to finding two numbers beta and gamma whose sum is 9 and whose product is 14. Can you conceive this number? Yes, they are nothing but 7 and 2. Can you see that 7 plus 2 is 9 and 7 to 2 is 14? Thus, beta is equal to 2 and gamma is equal to 7 are the other two roots, and that is what the answer is, because one of the root is already given, minus 9, and there are three roots in this cubic equation. That's why the other two roots are 2 and 7. It could have been written vice versa, does not make any difference. It could be beta is equal to 7, gamma is equal to 2. Anyway, it does not make difference. Thus, the two roots which are required to be found in this fill in the blank kind of quotient are rather 2 and 7. Aren't they? And that completes the discussion of this question. Well, this is the fifth question, and again, fill in the blank kind of question. You have to find the value of this determinant. It was asked in I.I.T. JEE 1988. And you can see that if I write down the determinant based upon a property which was property 5 as such in the previous lecture, 1, 1, 1, A, B, C, A square minus BC, B square minus CA, C square minus AB, right? And you have to find the value of this. Now, there is a property that we have discussed in the previous lecture, that is when any column or any row for that matter is expressed as sum of expressions, sum of numbers or sum of algebraic expressions, then it can be broken down into two determinants where the other two columns will remain same, but this would be distributed into the two determinant. This column would be distributed in the two determinant. Now I apply this, you will understand this very comfortably, I guess. So I write it down over here itself, that is, this can be written as equal to determinant 1, 1, 1, A, B, C, and A square, B square, C square. Can you see that I have taken the first part of third column in the first component determinant? And now the second determinant would be minus, why minus? Because there's a minus sign, so I can take common basically. And the second determinant would be, needless to say, would be again 1, 1, 1, because these two columns should be replicated, These two columns are not being distributed, so they'll be in both the determinants. And thus, you can see that ABC also occurring in it, and AB, BC, CA, AB, BC, CA, AB. Now, to find the value of this difference of two determinant, let's call the determinant, the first one as delta 1, this determinant as delta 1, and this determinant as delta 2. Delta 1 and delta 2. This is delta 1, this is delta 2. I am not going to manipulate determinant 1 at all. I am only going to manipulate the determinant 2, and I assure you it will come out to be identical to determinant 1, thus rendering the value of this given determinant equal to 0. Let me work upon the second determinant only. The second determinant delta 2, let me complete this delta 2 is equal to, well, the numbers are 1, 1, 1, A, B, C, B, C, C, A, A, B. One more property of determinant that we have discussed in the previous lecture, on the first lecture, was that I can take any factor common from any of the row and any of the column. So I go for 3 steps in one stroke. I take A common. I take ABC common rather from the third column. From the third column, I take ABC column common. If I take ABC common from the third column, so it becomes ABC and determinant. The first two columns would not be affected at all. That's why 1, 1, 1, A, B, C, and becomes 1 upon A. Can write here to save a space. 1 upon A, 1 upon B, 1 upon C. Isn't it? Now, in the next step, I multiply A in the, now I can take it inside and multiply it too, but I do it differently. Now I have taken common from the column. I am going to distribute this A, B, and C separately to these 3 rows. Now understand this step for a while. If you require, you may pause the video for a while after I complete this step. That is, in the row 1, I am going to multiply A, In the row 2, I am going to multiply B, And in the row 3, I am going to multiply C separately. A I am going to multiply in the row 1, B I am going to multiply in the row 3, and C I am going to multiply in the row 3. B in row 2, sorry. Now you can see that you can match it with a color. A I boxed with a white, so I am going to multiply in the first row. B I boxed it with orange, so I am going to multiply in the second row. C I am going to multiply in the third row. Now once I complete this step, you can see that what is going to happen. The same determinant will become A square. A is getting multiplied in the first row. So A square 1. B is getting multiplied in the second row. So it becomes B square 1. C is getting multiplied in the third row. That's why it becomes, oh, it has taken it out, b square 1 and c square 1. Now, there's yet another property of determinant which says that swapping any two rows, swapping any two rows or any two columns, like I swap column 1 and column 2, so it will bring in a minus sign before, right? So if I do that, then I can symbolically write it as column 1 swapped with column 2, right? Let me write it slightly here so that I get a space here to write, and this becomes what? You know, this becomes a square, b square, c square, a, b, c, 1, 1, 1 with a minus sign before. Why minus sign? Minus sign because swapping of any two columns brings in a minus sign before the determinant. Now, again I go for a swapping and I swap column 1 and column 3. I swap column 1 and column 3. This is how I'm going to do that. Now, this can be symbolically written as C1 is swapped with C3, right? And what do we get? You can see that. Again, I'll get a minus sign. So this minus and minus will become plus. That's why there's no need to put the sign over here. It will become 1, 1, 1, A, B, C, A square, B square, and C square. Can you see that? Can you see that it is again delta 1? This delta 1, I have started manipulating delta 2. Can you see that? I was manipulating delta 2, but it has finally become equal to delta 1. You can see that I'm undoing this, right? So that's why this is equal to delta 1 itself. Since delta 2 and delta 1 are equal, that's why the difference would be nothing but 0. So my answer would be 0 here, and that is the answer. You can see, right? This is what it is. Okay, that completes the discussion of this question. Well, this is the sixth question, and again it is a fill in the blank kind of question asked in JEE 1993. Now, for this question, I discuss some background of the logarithm. You know that log a to the base b can be broken down into log a to the base c upon log b to the base c. That is, any new base can be introduced which is legitimate, which is neither 0 nor 1 nor negative, because base cannot be 0, 1 or negative. Any new base can be introduced, and the original argument of the log will be a log in the numerator, and the base of the original log would be the argument of the log in the denominator, and any new base can be introduced. If I introduce the base, let's say e is a special number, as you know. It can be written as log a to the base e upon log b to the base e, where e is nothing but 2.71828. The beauty about this base is that this is known as natural log, and thus we have a very simple symbol for this, and simple symbol for this is, you know, ln a upon ln b, that is natural log. Read it in the reverse order. It is ln, but read it natural log a, natural log b, you know. So thus I don't have the obligation to write the base once it is base is E, and we can write it as natural log, not log, but ln. So thus finally, log of any number to the base any number can be written as ln of argument upon ln of base. So let us start with the determinant given. This determinant which is given is 1 log y to the base x log z to the base x log x to the base y 1 and log z to the base y log x to the base z log y to the base z and 1. Let me pull it down slightly. Okay, this is what it is. This is the determinant given to us. Now, using the discussion that I have done here, the same determinant can be written as 1 ln y upon ln z, ln x rather, ln z upon ln x, ln x upon ln y, 1 ln z upon ln y, right? And the third being, let me pull it down slightly to write the third also, that is ln x upon ln z, ln y upon ln z and 1. Now you can see that I use the property which I used in the previous question, that is any number can be taken common from any row and any column. I take 3 in one go itself. From the row 1, I am going to take common ln x. Understand that 1 by ln x rather. From the row 2, I am going to take common 1 by ln y. And from the row 3, I am going to take common 1 by ln z. You can see that from the row 1, 1 by ln x. What? 1 by ln x I am going to take common. From the row 2, 1 by ln y I am going to take common. From row 3, I am going to take common 1 by ln z. Now I undo that so that it does not create any confusion. Right? So the same determinant becomes 1 upon ln x, ln y, ln z, and determinant would be ln x, ln y, ln z. Can you see that? Once I take ln common, so here there is nothing in the denominator. That's why it will multiply with ln x. Out here it will become ln x, ln y, 1 by ln y has been taken common, ln y, ln z. In the third, 1 by ln z is taken common, 1 by ln z. That's why ln x, ln y, ln z. Now you know that if any two row or any two columns are identical, then the value of determinant vanishes. Here all the 3 rows are identical. It has all the more reason to vanish, and thus this vanishes. And thus the answer is 0. Right? And that completes the discussion of this question. Well, this is the 7th question, and it is given that determinant is a function of x. Then what is the value of f100? And it was asked in JEE 1999. So if I write the determinant, So determinant is, which is fx after all. Okay, fx is, let me write the third row first. It is the longest row. That's why let me write the third row. It is 3x, x minus 1. It is x minus 1, x minus 2, and x plus 1, x and x minus 1. So this is a long statement. Let me write the first two rows also, which is simple. 1 x, x plus 1. The second row is 2x, x minus 1, x plus 1 into x. Now, from a property of determinant, you know that if I can afford to add any row to any row, in fact, multiple of any row to any other row, it will not alter the value of determinant of the same thing can be done with the column also. Okay. Multiple of any column can be added to another column without altering the value of the determinant. What I do here is I add in column 2 column 1 as well. This is how I express it symbolically. The column 2 is modified by adding to this column 1. So what I'm going to do is I'm going to add this column to this. So it will no way alter the first column because it is going to get added to the second column. If I do that, what do we get? If I do that, what do we get? You can see that this becomes equal to, that is, the first column will remain intact. That is 1, 2x, 3x, right, the other here, maybe 3x, x minus 1, and the second column. Now, it is very simple to write. It is 1 plus x. It is 1 plus x because column 1 is being added to column 2. You can see that. Right. Out here, you can see that column 2 was already, what was this? This was x square minus x. When 2x is added to this becomes x square plus x, which is x plus 1, isn't it? So this becomes x plus 1. Let me undo that so that maybe I can keep it, I can rub it off and create a space for this. It was primarily x into x minus 1 which I manipulated. You may pause the video. For whatever I have done, I have rubbed it off. Now, when this would be added to this, what is going to be? It already is what? X was there, and inside that was x minus 1 and x minus 2, which was x into x square minus 3x plus 2, and added to this is what? That is 3x x minus 1, where I can take x common. I get x square minus 3x plus 2 plus 3x, so it will become x square plus 2. Doesn't it become? Okay. That is, I take x common, it will add 3x minus 3, 3x minus 3. 3x will make it 0, minus 3 will make it minus 1. Will it? Right. Minus 1, which can be factored into x minus 1. X minus 1 into x plus 1. Can't you see that? This can be written as x minus 1 into x plus 1. Is it neat enough? right? And third column I am copying simply. Third column I am copying, and the third column is x plus 1, right? X plus 1 into x and x plus 1 into x minus 1. Now, you can see something happening. What? You can see that the column 2 and column 3, column 2 and column 3 are absolutely identical. 1 plus x plus 1, x plus 1, x plus 1, x minus 1, x plus 1, x plus 1, x minus 1, which are identical. That's why this vanishes. And this vanishes identically for any value of x, because x is not mattering here at all. That's why it is fx is identically. Three lines means identically for all value of x 0. That's why the value of determinant is 0 and correct answer is A. That completes the discussion of this question. Well, this is the eighth and last question for today's lecture, and it is given that there is a determinant in the containing x, powers of x, and equated to 10. Of course, this is a polynomial equation, and looks like this polynomial equation will be having degree 6. You can see that the principal diagonal, you can see the principal diagonal. All these three will get multiplied, and that's why x cube will multiply with x square with x. That's why 6-degree polynomial it is. And they're asking the number of real roots of this equation, right? So you can see that I can copy the determinant over here, and this determinant is x square 1 plus x cube 2x 4x square and 1 plus 8x cube. And this is the nice question. JEE 2016 was one of the toughest paper, I guess, I was told. And 3x 9x square 1 plus 27x cube. You can see that again the third column appears to be addition of two elements. That's why this determinant can be broken down into sum of the two determinants, as I done already in the question. The first determinant would be x, 2x, 3x, x square, 4x square, 9x square, and 111. And the second component determinant after breaking down would be naturally x, 2x, 3x, x square, 4x square, 9x square, and x cube, 8x cube, and 27x cube. Now, there are plenty of factors which are common in both the determinants. In the first determinant, I take x common from the first column rather, x square common from the second column. So the first determinant becomes, I can slide the cursor slightly down so that I can write it over here, right? So first becomes, I guess, x I am taking common from here. Let me write with different color. And x square I am taking common from the second column. The overall common is x cube, and determinant becomes what? 1, 2, 3, 1, 4, 9, 1, 1, 1. Isn't it? Right. In the second determinant, if you can notice, I can take common x from the first column, x square from the second column and x cube from the third column. X cube from the third column. So in that way, the common here would be x raised power. Here I'll take x common, x square common, and x cube common. So here I'll get, there should be a plus sign over here, plus sign. Here I'll get x cube out, and I'll have 1, 2, 3, same as before, 1, 4, 9, again same as before, and over here I get 1, 8, 27. 1, 8, 27. Right? 1, 8, 27. Now I go for operation in this. I swap column 1 and 3, 1 and 3 over here. So in the first determinant, I'm going for the C1 squared with C3. So this becomes x cube, and we have the determinant 1, 1, 1, 1, 4, 9, and 1, 2, 3. Isn't it? I can swap, but I'll get a minus sign before. Remember that. So there'll be a minus sign over here, right? Plus, now there's a beautiful step. I take 2 common from the second row and 3 common from the third row in the second determinant. 3 common in the third row. So when I do that, I take 2 common in the second row, 3 common in the third row. What do we get? We get 6 out. That's why this becomes 6x raised to the power 6, and determinant would be 1, 1, 1, 1, 2, 4, because 2 has been taken out as a factor. And here 3 has been taken out as a factor. That's why 1, 3, 9. Now, I go for one more operation, that is I swap column 2 and column 3, that is C2 and C3 are being swapped in the first determinant. So again it will bring a minus sign, so it will become plus, so x cube, and determinant would be 1, 1, 1, 1, 2, 3, 1, 4, 9. Isn't it, after swapping? And here it will be plus 6, x raised power 6, determinant 1, 1, 1, 1, 2, 3, 1, 4, 9. Can you see that both the determinant become identical now? So thus I get the equation as x raised power 3 plus 6x raised power 6 as common, and determinant would be, what? The same, because they are same in both. 1, 1, 1, 1, 2, 3, 1, 4, 9, and is equal to 10. If you've forgotten that, I have not been writing this, but you can see that this is equal to 10 here given. All right. Let me proceed. Now, this determinant can be expanded separately from the rule of Soros or whatever. So maybe I can do it in a different color. This determinant is 1, 1, 1, 124, 139, and two columns can be written, two columns can be repeated for the application of Sorus rule, that is 1, 1, 1, column 1 being repeated, 1, 2, 3 being repeated. Now you know the rule. All the three principal diagonals, this, and this would be written positive, where all the secondary diagonals would be written negative. Agree? And thus you can see that the value of this determinant would be what? Would be 1 into 2 into 9, that is 18, plus 1 into 4 into 13. So that is 52, plus 1 into 1 into 3, that is plus 3. And minus secondary diagonal is 2, secondary diagonal is 1 into 4 into 3 minus 12, minus 9 into 1 into 1 is 9. That becomes equal to what? That becomes equal to, I think there was a mistake, because when we are multiplying the principal diagonal, first one is 9 to 2, 18, second one is uh, 1 into 4 into 3. So that is 4 only. Probably the mistake was because of the fact that I might have written the 3 very proximate to this. I read it as 13 in the beginning. Okay, anyways. So this is 4. So that this is equal to 2. So my equation becomes twice of x cube plus 6x raised power 6 is equal to 10. Let's assume, let us assume t x cube rather, x cube is equal to t. So I get t plus 6t square is equal to 5. I get 6t square plus t minus 5 is equal to 0. I factor it and get 6t minus 5 into t plus 1 is equal to 0. Thus, t is equal to 5 by 6, comma t is equal to minus 1. Remember that t is nothing but x cube. We require to find the value of x. That's why x would be 5 by 6 cube root of this, comma x would be minus 1 cube root, which is minus 1, because we are supposed to take only the real cube root. Had we wanted the complex one also, so we would have got complex cube root of unity minus unity also. But since only the real root is required, so there are only two answers. Thus, the answer to the integer type question would be 2, because it was written clearly. You can see that here. It was written very clearly, x belonging to real number. That's why real solutions are only 2 in number. So 2 is the answer. And that completes the discussion for today's lecture. We'll see you in the next lecture.